The Interested Reader podcast is about exploring the world beyond the textbook. We'll cover many lessons in math, physics, and astronomy, and then delve into the mysteries of the universe. Physics is fun, people just don't know it, and I want to change that. I want to spark your curiosity about the world around you and ignite your passion for exploring and questioning. I'm your host, Sarah Tyke. Come with me and let's take a random walk into the world reserved for the interested reader. Hi everyone, welcome to the first episode of the Interested Reader podcast. I'm very excited to be starting this journey with you, so let's get started. Today's lesson is going to be about units and unit analysis, and then we'll talk about one of my favorite units, that of time. So here we go. First of all, units. Why are they important? Units give meaning to numbers. It doesn't do you much good to solve an equation and just have a numerical answer, 5, 10, 23. You need to know, what do those numbers mean? And that's where the units come in. Are we talking apples? Are we talking oranges? Pounds, kilograms, newtons? So there are two major systems of units, the English and the metric system. And by now we all know that the US is one of the only countries that uses the English system. The other two are Liberia and Myanmar. So for this podcast, I'll be using metric the whole time. Our basic units will be meters, seconds, and kilograms. Now, kind of a thing to note here is that kilograms is often used as a weight. So we'll say things like, I weigh 74 kilograms, but that's not actually correct. Kilograms is a unit of mass. If you want to talk about weight, you're going to talk about force, which is in units of newtons. So technically, if you say you weigh 74 kilograms, you have a mass of 74 kilograms and you weigh 725 newtons. So in the English system, the pound is the unit of force, so you are correct to say that you weigh 165 pounds. In the English system, mass is measured in stones, so my mass would be approximately 11.8 stones. You can also use in the English system a slug, but obviously we're not going to be talking about stones and slugs in this course. We're just going to stick with kilograms. So we'll talk about unit analysis here real quick. This is one of my favorite techniques to just kind of do a quick check to see if your problem solving has been correct. So we just talked about force and how that is related to mass. So force is equal to mass times acceleration, and we have units of newtons. And acceleration is our constant acceleration due to gravity, 9.8 meters per second squared. So whenever you're talking about acceleration, your units will be meters per second squared. Mass will be in kilograms here. So if you wanted to say solve for mass, and you're just going through your equation, you better get something like kilograms. So say you just said, is that correct? Is mass equal to force times acceleration? Well, let's see. Do we have newtons times meters per second squared? And a newton is a kilogram times meter per second squared times. So already our units are looking pretty weird here. So we have kilogram, meter squared over seconds, fourth. Does that look like a mass? Nah, not really. So clearly that is not right. So clearly that is not right. So we can try again. Solving for mass. Our units here would be a newton per acceleration. And again, a newton is a force, so that's kilogram, times meters per second squared. That's a newton. And then we're going to divide that by our acceleration. And when you do all this, you can do the whole thing out. So dividing by that means we're going to multiply by that. and our unit is kilogram. So there we can see we got the right units for mass, should be kilograms, so we know that this is the correct solution of that equation for mass. So again, just a quick way to look at unit analysis. You don't have to worry about numbers. You just kind of go through and see if your units work out correctly. Another example that I like to use that's pretty easy is velocity, distance over time. So again, velocity we all know is speed. So we're all familiar obviously with miles per hour or meters per second. You can do anything you want as long as it's a distance divided by time. And this is an equation that we're all solving all the time, even if you don't know it. So if you're trying to run across the street before oncoming traffic hits you, in your head you're solving, how fast do I have to go to cross the distance of the street in the amount of time before the car and I collide? And in your head you're doing this calculation, you're not even thinking about it. And you're thinking, I can't run that fast, I better wait. Or how fast is the car going? It's going too fast, I can't make that distance in that amount of time. So you're always doing physics, you just don't even know it, and you're solving these equations just instantaneously. You don't even need it. You don't even need to know the numbers. You just do it and you know. So an interesting point about units that I've always found fascinating is that in 1999, the NASA Mars Climate Orbiter crashed into the surface of Mars because two different systems of units were being used. One team used the English system, one team used the metric system, and they didn't convert the two, and the discrepancy caused the engines of the orbiter to misfire, and it crashed right to the surface and cost $125 million. So you should always check your units. All right, so moving on to my favorite unit, that of time. I was told growing up that time didn't exist. It was a man-made construct. And that's always fascinated me because as you kind of go out through life, you think that maybe there's something to that. Obviously, we have natural cycles of time. The Earth rotates on its axis to give us a day. The Earth revolves around the sun to give us a year. And then, of course, there are the seasons. So these are all natural ways that time exists. And we've been measuring time since prehistoric times. Ever since you've got recorded history, people have been trying to measure time. There's a carving on a mammoth tusk that is said to be the constellation of Orion, the oldest known star map, dated to about 32,500 years old. But there is some debate over whether or not it's actually meant to be a star map or if it's just a coincidence. But the Egyptians have been known to be the first to develop sundials around 1500 BC. And calendars were first developed to align lunar and solar cycles. So the goal was to try to get an even number of lunar cycles per one solar cycle. So a lunar cycle is 1 month. It's how, as the moon goes through its phases, it happens every month. And a solar cycle is 1 year. So you try to get the even number of lunar cycles or months per solar cycle or year. And roughly speaking, a lunar cycle is about 29.5 days, and a solar cycle is 365.2 days. So when you divide those out, you end up with about 12.4 lunar cycles or months per solar cycle or year. But 12.4 is kind of a messy number, so we're just going to round it down and call it 12 months per year. And then that 0.4 fraction adds up over time, giving us an extra day every 4 years, which is our leap year. So, okay, so that takes care of, the broad scale of years and days, months. But why are there 24 hours in a day? That seemed always kind of arbitrary to me. So again, the Egyptians are credited with starting this idea of 24 hours. And they used a duodecimal and a sexagesimal base. So duodecimal is base 12, and a sexagesimal base 60. And today, our counting system is a decimal system, or base 10. So to the Egyptians, 12 was an important number. By then, they had determined that there were 12 lunar cycles in a year. And historians believe that 12 was also used because it was the number of finger joints on each hand, excluding your thumb. So there's 3 joints in 4 fingers each. So you could count to 12 using your thumb by counting your finger joints. And during this era, when sundials were being invented, Egyptian astronomers observed a set of stars that divided the sky into equal parts. So they had 18 that marked the night sky, with 3 each being assigned to dawn and dusk. So that gave us 24 stars. And the total darkness was marked by 12. So you have 12 hours of darkness. That would leave our remaining 12 for daylight. So between 1550 and 1070 BC, this system kind of finalized and got into place. So we had our 24 stars, 12 night, 12 day. That was our 24-hour day. All based on this base 12 counting system. So at this point, they now have the concept of a 24-hour day, but the hours were not fixed in length until the 1300s with the invention of mechanical clocks. Until then, the hours varied in length based on the season. So your summer hours were longer than in your winter seasons. Now, Hipparchus had suggested in about 127 BC this concept of equal length hours, but it never really caught on. People didn't have much use for it since they were mainly interested in agriculture and how the sun was moving. And that would not really matter if you had days, your equal length hours. In modern times, we have actual proof that time is relative. So Einstein came up with this idea of relativity, both special relativity and general relativity. And what this means is that time depends on your frame of reference. So if you have 2 observers that are moving relative to each other, you have this thing called time dilation. And the faster your speed, the slower the passage of time. And in special relativity, we were taking into account the observers moving relative to each other. In general relativity, Einstein also included the effect if an object was close to a large gravitational mass. So this seems very abstract, and how does it even apply to us? Who cares about theoretical moving observers? Well, our GPS satellites actually have to correct for these relativistic effects. So the satellites are moving relative to us. If we say we're stationary on Earth, the satellites are moving. So that means that their clocks would be slow by about 7 microseconds. But they're also being affected by Earth's gravity in a manner that's less than us at the surface. So we feel gravity stronger at the surface of Earth than these satellites that are way above us. So that would make the satellite's clocks fast by about 45 microseconds. So you take these into account and you end up with a discrepancy of about 38 microseconds per day. And after only 2 minutes, that would give these satellites, they would be giving us a wrong location if they didn't correct for it. So if you leave it unchecked, after 1 day, your location would already be incorrect by 10 kilometers. So that relativistic effect is a very real effect that needs to be taken into account on these satellites. So those are just a couple physical examples of how time is not even constant. But then you also have this physical or the psychological perception of time. So we all perceive time differently. I know when I'm at work and it's that last hour, it just drags by, like it goes so slow, and you feel like you're working for hours and hours, and you look at the clock and it's been 10 minutes. And then you're at home and it's your last couple hours before you have to get ready for work, before you have to go to bed. And those hours just fly by. So we don't even experience time in a constant manner. We all experience it differently. So what really is time? I mean, is it even constant? Does it even exist? We've shown it's all relative. And as Einstein even said, time is an illusion. I hope you enjoyed this episode and are inspired to question and investigate the world around you. Let me know what you're thinking about. You can contact me through the website, theinterestedreader.com, send me an email at sarah@theinterestedreader.com, or join the Interested Reader group on Facebook. I'll see you at some later time tea, where T is greater than T naught, and T naught is equal to now. Thanks for being an interested reader, and I'll see you next time.